problem number 4. So for problem number 4, you have a situation like this. This is number 4. Okay, so for number 4, this one says that we're going to have a block that's attached to a rod that is fixed at a point, which I'm going to call the pivot. And there's a bullet that's traveling towards the block, and it says that the bullet is traveling at some unknown speed, which I'm just going to call v naught. And the mass of the bullet is 0.010 kilograms, and the mass of the block is 1.5 kilograms. So the question is, first of all, or let's actually talk about what actually happens. So the bullet is going to embed itself within the block. What type of collision is that when they stick together?
Inelastic.
Completely inelastic. So the bullet is going to embed itself in the block, and then the bullet block system is going to swing up to some altitude. Okay. And then what is it going to do? Once it reaches the maximum altitude that it's going to get to, what is its speed for 1 instant? 0. And then what does it do?
Swing back.
It swings back, right? So this is why it's called a ballistic pendulum. All right, they actually told you what the altitude was above the lowest point. So they told you that the altitude above the lowest point is actually 0.4 meters. So take a look. So now, here's the thing. What we want to find out from this information is how fast was the bullet moving before the collision occurred. Now, this is a 2-stage problem. The reason I say this is a 2-stage problem is because there are technically 2 distinct processes going on here. The first process is the collision of the bullet with the block. The next process is the swing of the bullet block system from here to here. Does everybody agree? Now, what did I mention at the beginning of the review? Anytime something collides with something else on this test, what is going to be conserved? Is it energy or is it momentum? Momentum. So, we're going to break this problem up in half. We're going to deal with it with 2 different processes. The first process, which I'm going to call process number 1, or P1, is going to be the collision with the block. So there's the bullet right before it collides with the block. It's traveling with a speed v naught. And so this is the initial for process 1. And the final for process 1 is this. The moment right after the bullet stops within the block and the bullet block system begins to move, that is what I'm going to call the final for process 1. So the process 1 is the collision of the bullet with the block, and then the subsequent motion of the bullet block system after the bullet has stopped within the block. Okay. So the swing part of it comes later. That is what I'm going to call process number 2. So does everybody see how I got this? Okay, this is my initial picture, this is my final picture. All right, so momentum is going to be conserved because remember, in a completely inelastic collision, where 2 objects stick together after collision, you know that momentum is conserved, energy is not conserved. You're going to be losing some energy. What is that energy turning into? Heat. So the bullet, as it digs a hole through the block, it's going to actually feel a very large frictional force inside of that block, and that's going to heat the bullet up and also the block a little bit inside. And then also sound, right? So this is, you're going to hear it, so that's some compression wave in air, so that's going to be some form of energy as well. So take a look at this. What we're going to do is we're going to say, what is P initial for the system? Remember, this is a system here. So I have to add the momentum for both objects within the system to get the total momentum of the system. So the P initial, that's going to be the mass of the bullet, so 0.010, times the initial velocity, so v naught. Plus, is the block moving initially though? No, so it doesn't have any momentum. So that's the initial momentum of the system before the collision occurs. Now, do I have any final momentum after the collision occurs? Yes, and since it's a completely inelastic collision, what happened to the masses? Does everybody agree they combined and then they move as one? So what can you do with the masses at the end? Add them together. Very good. So that's going to be the 1.5 kilograms of the block plus the 0.010 kilograms of the bullet. That is the total moving mass now. So total, after the bullet embeds itself in the block, that's how much mass is moving afterwards. Okay, but that's not momentum, that's just mass. So to get momentum, I have to do mass times velocity, right? So this would be the mass times the final velocity of the bullet block system. Does everybody agree with that? So now we can write it as 1.51 times V final. And I don't know what V final is. What does V final represent? It represents how fast is the bullet block system moving the instant right after the collision. Okay. So we don't know what that is. So very important that you note that this V final is not when the bullet block system has reached the top. Remember that that is process number 2. Here we are talking about process number 1, which is the collision of the bullet with the block. Okay, so since momentum is conserved during this collision, and every collision actually, what we can say is P initial is equal to P final. Okay, so I'm going to say 0.010 V naught is equal to 1.51 V final. Does everybody agree with this statement? Does everybody see that? I'm setting P initial equal to P final. Now, I've exhausted everything that I could do in process number 1, because even if I tried to do energy initial equals energy final, that would be the wrong way of approaching it. Why? Because energy is not conserved during the collision. Okay. So now I have to go to process number 2. So take a look at process number 2. So process number 2 is the swinging part. So I'm going to start like this. Does everybody agree that process number 2 begins at the same moment that process number 1 ends? Does everybody see that? So here's process number 2, and it's basically, it's the beginning of it, initial, is the same as the final for the previous stage, okay, without any discontinuities. So I have V final. Notice that for initial I'm using V final. Why? Because it's actually the V final for stage number 1. So I'm still using the same VF, same symbol. Now, at the end, I swing up to some altitude. And here's the lowest point again, remember? And the altitude is 0.4 meters as given. I didn't have to calculate that, that was actually given. The bullet's still inside, by the way. What is the speed of the bullet block system at the max height?
0.
0. Excellent. So now, during this process, is there any collision going on? Or is it just a swing? It's just a swing. Gravity is the only force doing work in this scenario, and gravity is a conservative force, so it's going to conserve the total energy of the system. What happens to the altitude of the bullet block system as time goes on? Altitude goes up. Does everybody agree? So potential energy should go up, but kinetic energy should go down so that the sum remains constant. Does everybody agree? So here, energy will be conserved, okay, as long as we neglect everything. So, U initial, let's talk about it. Does everybody agree that this is not necessarily the ground? Does everybody agree? The lowest point is not necessarily the ground. But does everybody agree that I mentioned in class that you can actually set your potential energy to 0 anywhere you'd like? Does everybody agree? So for a pendulum problem, usually you set your potential energy to 0 at the lowest point. Okay, so here's my U equals 0 now. That's the lowest point. So what would be my initial potential energy? My potential energy when I'm here? 0. Excellent. So 0 joules. What about kinetic energy? Do I have any kinetic energy here? Yes, I do. That's going to be 1/2 the mass. But which mass? Bullet, block, or both together?
Both.
Both together. Very good. Because remember, bullet's already inside, right? And so they're together now. So that's going to be 1.51. That's the total mass. Notice that that's the M1 plus M2 that I used over here on the right side. So, and then times Vf squared. And again, it looks strange because it's the initial kinetic energy, although I'm using V final. You have to remember that that V final is actually the V final for the previous stage. That's why there's a V final. Okay, so that's my kinetic energy initial. Okay, now, what about kinetic energy final when I get here? Any kinetic energy there? 0, because for 1 instant in time I'll be at rest. And then what about my potential energy final? Do I have any? Yeah, I'm elevated or I'm displaced away from the U equals 0 line. Therefore, I will have some potential energy. It took some work to get up there. Okay, so we're, in this case, some energy transformation. So potential energy, or kinetic energy turned into potential. So take a look. That's going to be mgh. So it's going to be m So m is here together with the bullet and block. So 1.51 times g, which is 9.8, times the altitude, which is 0.4. Okay, does everybody see how I got all of these ingredients? Yes?
Can you do the kinetic initial again?
1/2 mv squared. That's all I did. So it's 1/2 times the mass of both of them, the bullet and the block, so 1.51. That was the same sum of masses that I used over here. And then times v final squared. Yeah. V final is the speed that the bullet block system had immediately after the collision.
So what's
Stage
the
one.
F above the VF square? The VF.
Which one?
Do you have it like on the upper right corner of the square?
This is final. So basically final for the initial stage. So
Got it.
don't worry about that.
You're
This
just
is going to
showing
be final.
Gotcha.
Yeah. Okay, so does everybody see how I got all of these? Does everybody see that? Okay, so now what I'm going to do is I'm going to go ahead and insert this into the conservation of energy equation. So this is going to be U initial plus K initial equals U final plus K final. So my U initial in that case was 0. My K final was also 0. Does everybody agree with those two statements? So it becomes particularly easy in this case. Kinetic initial is just 1/2 the mass times V final squared. And then U final is mgh. So 1.51 is the mass times g is 9.8, and then the altitude is 0.4. That's given. So the 0.4 is actually a given quantity in the picture. You can see it. What happens to the mass? The mass cancels, you can see. Can I now solve for VF? Yeah. So VF is going to be the square root, once I do the algebra, 2 times 9.8 times 0.4. All right, so let's see what I get for that guy. Let's take a look. So that's going to be 2 times 9.8 times 0.4, and then we're going to take the square root of that guy. 2.8 meters per second. Now, question, is that the initial speed of the bullet? What does VF represent?
The final, or the impact speed.
Right, so basically that is the velocity right after the collision occurs. That's what it means. But that's not the velocity of the bullet before the collision. How would I get the velocity of the bullet before the collision if I knew how fast the bullet block system was moving immediately after the collision? How would I do that? Plug it back into momentum. That's why we had to use momentum conservation. So now we take that VF that we just got with energy, and we're going to put it in right here, 2.8 meters per second. So that's going to be 0.010 times V naught is equal to 1.51 times 2.8. And now all we have to do is divide, and we've got it. So when we divide, we end up with, I believe in this case, 422.
424.
424? Okay. So 424 meters per second. Okay, so does everybody see how we got this one? So this is like a two-stage problem where you have to use both chapters 9 and 10. 9 for momentum and 10 for energy. Okay. All right, so let's take